Cray Inc. is one of our gold supporters. We're very, very happy to have their support for this conference. They have provided a tutorial. This is the second of 2 BOFs they've run. In addition to their sponsorship, they have really been critical to the success of this conference so far. And I've known Steve for a while now, but I want to read off a piece of paper so that I get this right. Steve Lyness has been with APRO for some good amount of time and is now with Cray by virtue of Cray's acquisition of APRO. And I will say that as a longtime observer of the industry, I think the Cray-APRO merger makes a tremendous amount of sense. I think it's very, very interesting. I think it's going to help Cray be successful. I think that the merger brings some interesting characteristics, tools, and capabilities to the people that have traditionally sold products under the APRO banner. Steve has been responsible for solutions architecture for InfiniBand systems, and Steve and his teams have designed numerous HPC solutions with a variety of interconnects and a variety of topologies, and yet you have hair. With no further ado, Steve, thank you very much. Take it away.
All right. Thank you. All right. Thank you very much. So this is the first time I've done a birds of a feather with such a large audience, right? I've done these kind of all over the world, and there have always been little quaint rooms with, 15, 20 people. But we do want to make sure that we make this very interactive, right? It is a birds of a feather, right? So it's not a Cray pitch. It's about talking about topologies. It's talking about networking. If you have questions, if you have things that you want to share with the group, right? That's really what a birds of a feather is about. So I have to include this, right? Safe harbor statement. Anything I say talking about the future, Cray holds no responsibility for it. So one of the things that I'm going to do is talk about the relative costs. Right? So to be able to do that, I need to set the appropriate stage, which means to talk about what the servers look like. So all of the systems that I talk about and the percentages are based on Cray Greenblades. Right? Now, inside of this, we can really skew the numbers depending on how we configure the individual nodes. Right? So there's high-end nodes, middle, typical nodes, and low-end. Right? So here I'm trying to show what I think are typical high-end, right? So we have at the top dual socket Ivy Bridge, right, with 12 cores, 2.7 gigahertz. That's really the top bin for Ivy Bridge. You would probably put 128 gig of RAM and a FDR InfiniBand and a terabyte hard drive, right? Typically, though, you're not going to go with the top bin, right? So what I've used for all of the analysis is one of the processors that is more commonly used, right? So this is the E5-2670, right? V2, the Ivy Bridge 10-core, 2.5 gigahertz. Drop the memory down to 64 gigabytes per node, right? 1866, 8 gig DIMMs, and the hard drive, right? We didn't go quite down to the low end because, again, this would skew the numbers. So, you could honestly go as low as the 2450, right, which is the Ivy Bridge 8-core, 2.5 gigahertz. Some of the other assumptions as we did the analysis is we assumed everything was air-cooled, right? We're not putting any of the water-cooled technologies in here. Everything is 208 three-phase. We're not doing 480. Gigabit Ethernet networks for operations and management networks, and then a full software stack, right? So this is looking at the overall numbers of a full solution, right, with cluster management, Red Hat Enterprise Linux, Intel Cluster Studio for compilers, debuggers, and the performance analyzers, and then Slurm or a similar open source scheduler. Right? So this is just a look at the management network, right? How we would typically lay these out to be able to do the initial provisioning of systems as well as subsequent management, right? So there's a GigE connection assumed to every node within the cluster, and then a management network that would connect in things like management ports on subracks, the management ports on the Ethernet or InfiniBand switches, and then also to the service nodes, like the login nodes or management nodes. So one of the big things that we start talking about when we start designing systems is, not only what are we going to use for the interconnect, right, but also what is the topology going to be, right? It's very easy today to have kind of standardized on InfiniBand, right? I mean, we can debate whether it should be QDR or FDR. We can talk single rail or dual rail. But for today, I'm trying to limit the analysis to single rail InfiniBand, and FDR is obviously the most popular today. And then there's different topologies, right, that we can talk about, right? Single and dual rail fat tree, right? This is the most common one that everybody seems to be doing, particularly for any of the larger systems, right? We tend to head towards something that we're comfortable with, something that we know is going to work, something that should meet pretty much all requirements, right? With distributed core or large director class core switches. Some other options, though, would be to have an oversubscribed tree. Right? So as Jay mentioned earlier, right, the Stampede cluster is almost full bisectional bandwidth. It's 5 to 4 oversubscribed. But a lot of people are seeing that they don't even need even that high of a level of subscription. Right? They can do 2 to 1, 3 to 1, 4 to 1, really depending on the applications that they're running and the average job sizes that they're using out in the system. Then we also have other topologies, right? Inverted trees where we're putting large switches at the edge, right? And oversubscribing to smaller switches at the core. Islands, right? Where we're able to create full bisectional bandwidth groups of nodes, right? And then loosely couple those together, a lot of times only for storage access. And then also Dragonfly topologies that are used for not only InfiniBand, but some other interconnects. Right. So the first one I wanted to look at was a fat tree, right? So in this instance, it's a 1,600 node cluster. 1,800 node cluster with the green blades that I showed earlier. So what we end up needing is about 102 FDR InfiniBand switches out at the edge, and then 6 324 port or 3 648 port switches at the core, and then we can connect in our storage off of the core. But as we look at the overall cost of a fat tree, right, as a percentage of the system, we can see that it will vary from around 12% of the cost of the system at very low node counts, right, at 32 nodes, all the way up to well over a third of the system, right, 34 or 35%, when we start getting up to 2,000 nodes or more, right? And you can see 2 inflection points, right? One is right around down by our 32, and one is just above 512. So I'll ask a question. Does anybody know why those inflection points exist? You're all eating and half asleep. Got it. Okay, no one? All right. So the first inflection point is when we start going over a single switch, right? So the typical InfiniBand switch is 36 ports. So once you go above 36 ports and you start adding the second layer, the overall percentage goes up. The second inflection point is at the largest switch, right? So 648 ports from either Intel with QDR or Mellanox with FDR is the second inflection point. Once you go to 649 nodes, right, you have to start adding yet another layer of switches, which is why you get that ramp that starts going up. And if you go even above that, and I forget what the number ends up being, but it's 648 times 18, whatever that ends up being, 10,000, 11,000 nodes, then you have to add yet another layer of switches, but I didn't do that for this analysis. So if you look at the overall percentages, right, so I broke this up into different categories. Compute nodes, right, service nodes, right, so these are your management nodes, your login nodes, sub-management nodes, so if you're doing large systems, you have nodes that are going to be helping with the provisioning of the operating system, right? InfiniBand, Ethernet, right? So there's your gigabit Ethernet operations and management switches. Software, right? So that's your cluster management, your compilers and debuggers. Infrastructure, so this is racks, PDUs, right? And then services, which are staging, integration, project management, all the services that are needed for a full end-to-end system. So if you look at the overall percentages, at 32 nodes, the InfiniBand portion is not all that large, right? It's around 12%. But as you start going up, you can see a little bit better visually at 256 nodes, right? The yellow section is quite a fairly significant amount of the dollars that are being spent within the cluster, right? And the interconnect, while very important, is not doing any real work, right? We want to spend most of our dollars on the pieces that are actually going to do the work on the compute, right? Or on the storage where we're going to be putting all of the data, whether it's the input or the output results. And then at 1,000 nodes, you can see that the InfiniBand has now grown to over 1/3 of the pie, right? So you're spending 1/3 of your capital dollars when you're buying a system on just the InfiniBand interconnect. And that's the HCAs, the switches, and the cables, right? That doesn't include any additional software that you might buy, right, as part of the overall solution for just the InfiniBand, like UFM or FCA, right? If you're doing collectives acceleration or you're doing fabric management down at the InfiniBand level. So the next one I wanted to look at was 2-to-1 oversubscribed fat tree, right? So taking a similar configuration, here we have 1,200 compute nodes, right? Some standard compute nodes, some GPU-enabled nodes, and the service nodes. And here we need 50 36-port FDR switches. Right? We put 24 nodes on each one of the edge switches. We do 12 cables down to the core. Now the upside obviously is decreased cost. Right? We either have less or no director class switches. Right? So we reduce the amount of dollars that are spent on switches, on cables, even on racks. Right? With these large director class switches, typically we have to do one for each rack. And we decrease the number of edge switches, right? So we only need one for 24 nodes with 12 links to the core. So we go from 67 edge switches with a fat tree down to 50 in a 2-to-1 oversubscribed. Now the downside is for jobs over 24 nodes, or about 480 cores in our example, our oversubscribed links end up being used for increasingly, right, to be able to run those jobs. So now we're setting ourselves up for potential congestion problems, right? Not only for IPC traffic that is being used for node-to-node communications that don't necessarily sit on the same edge switch, but also for storage traffic, right? So those 24 nodes have to share those 12 links to be able to get at the storage unless you put storage connections all the way out at every edge switch. So this means that we also have to have very careful placement of jobs. Right? So topology-aware schedulers like Sun Grid Engine or Slurm have the ability to localize the jobs based on nearest neighbor, right? So that we can help minimize the congestion. But we still have issues when we start overflowing into neighboring switches, or in worst case, when you start losing efficiency of the cluster and you have to start taking jobs and spreading them out across the entire cluster. One of the ways to get around it would be with large edge switches, right? A lot of times these are called inverted trees, right? So we're putting large InfiniBand switches out at the edge. So in our example here, we've got about 2,556 compute nodes. Right? We put 432 nodes inside of one of these subclusters, right, connecting to a 648-port switch. And then we can connect those large edge switches into smaller 36-port switches at the core. right? So instead of having large switches at the edge and small switches at the edge and large switches at the core, we've kind of reversed it. Now, our 432 nodes on one of these subclusters can run at full bisectional bandwidth. So it's only if we go above 432 nodes that we need to be able to go down to the core or if we're accessing storage. Right? Here's another example where we did a single island 2-to-1 oversubscribed. Right? It's got a 216-port Intel QDR switch at the edge, right, with 140 compute nodes and some I/O nodes to be able to access the Lustre clustered file system from a legacy storage, and then another connection to an IB SAN. This gives us about a 2-to-1 oversubscription into the core, but again, it allows 140 compute nodes, or about 2,240 cores, to run at full bisectional bandwidth. And then we tie the islands together with 36-port core InfiniBand switches. Right? Upside, obviously, is we do have full bisectional bandwidth on each one of the islands. So we do decrease some cost by reducing the number of switch chips, or the number of switches, inside of these island configurations. It also reduces the number of cables. The downside is that for jobs over a specific node count, right? And we had two examples. I think one was 424, one was 240, or 140 nodes, right? We become increasingly dependent on those island-to-island links, right? So we have to be careful that we're carefully placing jobs, right, out on individual islands, because if we start spanning islands, we start having significant increased probability of congestion. Another topology that is deployed is 3D torus. Right? So, for example, we've done San Diego supercomputer with a 1,000-node dual-rail 3D torus. It works extremely well for a lot of the codes that San Diego runs because they do a lot of nearest neighbor communications. Right? So here's a 1,200-node system. Right? We create 18 node points, so we put 18 nodes on a 36-port switch, and then we take 3 connections in each one of the 6 axes directions, right, creating a true 3D torus. So plus x, y, and z, and minus x, y, and z. Right? Upside, again, is decreased cost. Right? No director class systems are needed regardless of pretty much how large you're going to grow this system. You just start expanding in one of the 6 axes directions. Right? A 1,000-node cluster will decrease the cost of the FDR InfiniBand by over $1 million. Right? So that's a lot of money that can be spent on buying additional compute nodes. IB cost goes down from 28% to 22% of the overall system. Right? And if you look at that, you're looking at adding potentially 100 to 200 additional nodes into the system. Right? And we have very good nearest neighbor performance. Right? Even if you go off of the 16 or 18 nodes that you put on one of the points within the torus, as long as you can localize the jobs to be on a switch that is nearest neighbor to the one where the rest of the nodes are, right, you're still running at a single hop and you're able to get very good performance at reduced latency. The downside is that for large all-to-all communications, you potentially have a very significant number of hops. Right, to get from certain parts of that 1,000-node cluster to, say, the center, right, from an edge to a center, if you were to draw it out logically, right, we end up with up to 5 hops to be able to get from node to node. Right? If you have a very latency dependent and a lot of all-to-all, if you're cutting jobs up into very small chunks, those all-to-all communications become very important and very latency sensitive. So again, requires very careful placement of jobs. Right? It's very important to have a topology-aware scheduler that is able to localize those jobs and make sure that you're using those nearest neighbor nodes. The problem we run into, right, with all of these configurations is going to be efficiency of the cluster. Right? A lot of times we have issues where you run these jobs, and if you say, I want to wait, right, you can put in there that basically within the job queue, I want to wait until I can run this in the most efficient manner, being able to use nearest neighbor nodes, right? But reality is that could cause a fairly significant delay while you're waiting to be able to run that job. Another option is Dragonfly, right? This really minimizes the overall cost because not only are you reducing the overall number of switches, right? You're doing a lot of all-to-all connectivity, right? That is able to take advantage of things like adaptive routing, right? And this will scale to very large systems. The problem with Dragonfly, particularly with InfiniBand, is we need to do very complex routing algorithms, right? It's not as simple as being able to set up static routes like we typically do in InfiniBand. Now, as InfiniBand started to mature into its third and fourth year, right, the companies like Mellanox started building in some capabilities into the hardware to be able to do what they call adaptive routing. Right? But adaptive routing in InfiniBand is really more reactive routing. Right? It looks at the overall network, and when congestion starts to happen, then it tries to reroute, right, using an alternate path. But even then, if it has a second problem, right, on that alternate path, it starts to really create congestion issues because it only allows for a certain amount of reconfiguration of the system, right, and rerouting of packets. So what you really need is congestion look ahead, right? It's the ability to be able to route packets not only reacting to congestion problems, right, but also being able to kind of load balance across the entire fabric, right? So for Dragonfly, I use the Aries as the one that obviously I know the best, right? So this is the one from Cray. And you have the single packet, right, that's going to go from point A to point B, right? But not only will it send it over that route, but it'll actually bounce it off of a second route, right? And it'll even use a third route to get from point A to point B. And in fact, it'll actually use 4 different routes, right? So it starts utilizing all of the different links, even though it doesn't necessarily have to right up front, right? Because it's using the adaptive routing algorithm that Cray developed with Stanford. I don't know if anybody is here from Stanford. But basically what it's going to do is ahead of time, so if you look all the way up at the top, right? It's doing a lot of nearest neighbor communications every 10 cycles, and it's collecting information. So it's truly looking at the way that packets can be routed to distribute the data traffic evenly, right? So as the data packet comes in, it looks at possible routes, it determines the best one, and it does this on an every packet basis. Right? So looking at fat trees, right? In our first example, all the way on the left-hand side, right? This is a 512 node 512 node jobs that are going to run, and this was done at Sandia. Right? So they did this type of testing with the Dragonfly. And under really great conditions, right, under a totally quiesced system, you kick off 4 512 node jobs. Scheduler can nicely place them across the 2,000 nodes, and everything runs really well, and you get a total time of about 69 seconds. Right? But as you start running the system, things start getting segmented, right? So you can't sit there and necessarily wait for another big 512 node chunk. But with Dragonfly, you can see we go from 69 to 69.4. This is probably a little bit more typical of what you're really going to run into in real life, if not this one all the way over here. But this is more a real-life example, and we went from 69 to 69.7. And in the far right corner, they did a completely randomized set of nodes, and it ran at 70.9 seconds. Right? So the ability to place jobs didn't become anywhere near as important. So which one works for you? So one of the things that at least we do at Cray is we spend a lot of time with our customers, and whoever you have as your vendor needs to be able to do this as well. And maybe they are, or maybe you're doing it yourself, is understanding what your jobs look like, right? I mean, we saw some good information off of Stampede this morning, right, on job size and the frequency of jobs. So this is from one of our customers, right? The number of average processors, and in this case processors is cores, number of average cores that goes into an individual job. And as you can see from this example, right, 256 to 1024 is about the sweet spot. A lot of the other jobs are running that are 32 to 256, right? So there's not a whole lot of really large jobs that are running on their particular system. So then you look at the individual jobs and what percentage of the overall job queue, right? So this customer ran a lot of Gaussian, some VASP, MATLAB. Once you get past Velvet and once you get past NAMD, it really goes down pretty quickly. So when we started working on the analysis for them on where to spend the money, right? And we go way beyond just talking about the network, right? But we don't have enough time today to talk about balancing CPU core count and frequencies and memory capacity and memory bandwidth and I/O bandwidth and internal hard drives and trying to get all the right ones to maximize the dollars for the way that the system is being put together to go after the majority of the jobs, right? I mean, there's a certain amount of jobs that are going to want more memory, they're going to want more I/O bandwidth, but you can't always design the system to meet every instance, right? Sometimes their performance may have to suffer for that one job that's going to want to run over the entire cluster so that you can get more nodes to run more jobs for more users, right? Unless you happen to be somebody like Noah and you're doing weather forecasting, you want it to run full speed whenever you need it, right? It really comes down to where the right balance between hardware and software, right? So you start doing application profiling, right? Whether it's a known profile for a particular ISV application or you start doing instrumentation, right? To start gathering information on the percent of time that's spent in compute, the percent of time that is in communication, how much time is spent in I/O wait, right? Where the CPUs are just sitting there and spinning, waiting to get I/O. Right? System balance, again, between cores, frequency, memory bandwidth, memory capacity, and I/O. Right? So you start zeroing in on the two top bins. In our example, it was 33 to 256, or about 3 to 16 nodes, 257 to 1024 cores, which is 17 to 64 nodes. Right? So we start looking at those as the job sizes that we want to spend most of our money on as far as the interconnect and how much bandwidth we want to be able to designate. Right? We assume some amount of growth. So one of the things that we typically run into is we look at customer job sizes and they say, well, they only usually run up to 16 nodes. Well, the reason they only run up to 16 nodes is that when they run 24, then the performance gets a lot worse, right? In fact, sometimes you run it on a larger core count, you end up with a longer wall clock time. Right? Now, it could be any number of reasons. It could be the scalability of the individual application, right? You may be chunking up data into too small of pieces, or it could be that you have just limited them because of the I/O bandwidth that you gave them, right? So it may be a self-fulfilling prophecy that the application runs that they're doing is they only run it up to a certain size because you have designed your system that it limits the jobs to be able to run under that size or under, right? So you have to allow for a certain amount of increase, right? Whether it's, oh, now look, I've got more bandwidth, right? My application can scale better, so they'll start running maybe larger jobs. So we usually assume about a 25% growth in core count for the top applications. We start reviewing job communications, right? How much of the time is spent doing communications, whether it's all-to-all communications, right, in collectives, or whether it's nearest neighbor communications, or whether it's storage communications, right, and whether those things are being done in parallel or serially. Right? A lot of times we spend a lot of money saying, well, we need all of this IPC traffic, but we also need to be able to do storage, but a lot of times we're not doing those two concurrently. Right? We read data in, we do our processing and our all-to-all communications, and then we push our data out, right? So those things get done serially. So you don't necessarily have to have bandwidth that's going to cover the IPC and the storage simultaneously, right? And then we have to also look at packet sizing. So when I was at QLogic, we spent a lot of time looking at the effect of increase in node count in jobs, right, when you compared it to the requirements for I/O bandwidth and latency. So as you start taking data sets and breaking them into a lot smaller parts, right, and start spreading them across larger nodes, the message sizes typically go down very significantly, right? So bandwidth becomes less important. But latency is very important as you start getting the messages smaller and smaller, as well as message rate. Right? So we need to make sure that we're taking those things into account of what size data is going to be typically run, right? As well as what the science is going to require going into the next year or two, right? If they're going to much higher granularity on their data sets, we need to make sure that we're taking that into account when we're doing the overall analysis. Right? So then you start reviewing the available topologies, right? And then you start matching it to the number of topologies that we discussed before. Right? So conclusion, which one is best? There's no real answer, right? So this was something that came out of a HPC Advisory Council in Switzerland. It really, really depends. And I know everybody hates that answer. Well, what's best for me? It depends. It depends on your applications. It depends on your data set sizes. It depends on what percentage of the jobs are running at what different sizes, right? So the idea here was to hopefully give everyone some things to think about, right? Maybe we can talk about them if you have now some input, if you're not completely asleep. And, you know, really look at your specific requirements. But the one thing I would say is InfiniBand Dragonfly is really difficult, right? They came to the same conclusion that Dragonfly requires support for adaptive routing and congestion look ahead, right? And this is not supported by any existing hardware, which was InfiniBand at the time. That's the end of my talk. Questions, comments, your own experience?
Yeah, so I've got a question actually about the modeling. You know, it seems to me that high-performance computing is one of the few places where increasing supply always increases demand. And in fact, the increase in demand is usually greater than the increase in supply. Do you have you talked a little bit about, you know, the case of, well, people only usually hit 16 cores. You know, do you have any tools that you use in projecting what's going to happen to a workload as you get a bigger system?
So Cray specifically, we have a lot of segment specialists, right, that can go and look at codes, whether they're ISV codes or they can even comb through some of the custom codes. And they can look at the scalability and they can look at the data sets, right, and try to determine whether they're being limited because of something that was in the existing cluster and whether they'll be able to grow, or whether there is some significant limitation in maybe the code itself or what the code is trying to do, or maybe it's just the size of the data set, right? As you start to take those data sets, if they're too small and you break them up into too many different pieces, you spend more time trying to do I/O communications than you're doing CPU, and that's why you tend to get that ramp drop, right, where it takes longer to run on more nodes than it did on a smaller node count.
You mentioned that Dragonfly is a very complex algorithm. Now my question is very concrete. Do you know what is exactly complexity of Dragonfly algorithm? In measuring depends the number of nodes, and how that complicate your life, because high complexity means a lot of computation, slow down, and so on.
So one of the things that we do run into with the XC30 is that it has to have very specific configurations, right? The algorithm only works with very set node counts, very set number of endpoints, right, to be able to run those algorithms. It's not quite as flexible as InfiniBand is going to be. You don't have quite as many different choices, right? You can do, for instance, 64 nodes, but 65 becomes a little bit of a problem, right? Because you're creating a particular fabric look that really isn't supported by the adaptive routing algorithm. So it is limited in the different configurations that it can support. Makes my life a little bit easier because I don't have to have quite as many people looking at different ways of configuring it because it's preset. But it's a little more difficult because it's, you know, for somebody who has a very specific budget, we need to see how we can fit that in with those particular node count configurations.
At one time, a while back, there was research into randomized algorithms for routing to avoid congestion. Do you have any experiences with that?
I've seen some of the papers that were written on it, and seemed to be one of the things that was going to be extremely difficult to do because of the need to have things down inside of the silicon, right? I mean, you can't do endpoint routing, right? It can't be really destination routing. It has to be looking at source and destination, which obviously isn't good for InfiniBand. So I think one of the guys that was doing the 10 gigabit Ethernet over in the UK, Nodal, which unfortunately I think they closed house. They had really nice randomized algorithms for being able to send the data across. Unfortunately, they did it with 10 and 40 gigabit Ethernet. So it had lower bandwidth, higher latency, and it cost more than InfiniBand, so nobody wanted to buy it. So, but the algorithms themselves look really good. Those guys came out of the old Quadrix organization, and they had some really good ideas about how to do that, but the implementation was on Ethernet.
So are there any other questions? If not,
Nope.
let's thank Cray for lunch and thank Steve for the presentation.
Thank you very much.